Welcome to the exercises for Chapter 10, focusing on multivariable functions and differentiation. This first exercise is not about calculus per se. This is about working with matrices in NumPy and visualizing them in Matplotlib. This will be helpful for you to make sure that you really understand how to interpret matrices when you see matrix representations or image representations of two-dimensional functions and their partial derivatives. Okay, so start by creating a 5 by 10 matrix. That means this matrix will have 5 rows and 10 columns. So it's like a long rectangle shape in which the element of each matrix element in the ith row and jth column is defined according to this formula here. Now, for starters, I want you to create this matrix in a double for loop. So you loop over all the rows, and then you loop over the columns, and define every element in this matrix according to this equation for one particular value of I and j. If you're up for a bit of a challenge after that, you can try to recreate exactly this same matrix, but without using any for loops. That would be a slightly more advanced way of doing this if you've taken a linear algebra course, for example. If you're struggling with creating this without for loops, then don't worry about it. For loops are great. Okay, and then what I want you to do is print out the matrix as you see here. Now, here you see only integers, but this matrix actually comprises floating point numbers. So there's decimal points in this matrix, but just to print it out to make it easier to visualize, only print out the integers. Okay, so all of that was part one of this exercise. The next part is to visualize this matrix using PLT, so Matplotlib's imshow function. And you can see in this image representation, so in this picture, the negative numbers are mapped onto darker colors and the positive numbers are mapped onto lighter colors. Okay, and then I've used plt.text to write the numbers, to draw these numbers on top of each cell, each matrix element here. And I've also drawn this white line from this matrix element to this matrix element. There's no like deep mathematical theory behind this equation or behind drawing the line from this element to this element. This is really just to make sure that you are familiar with how to work with visualizing images corresponding to matrices in Matplotlib. Here you see the code. Here I'm creating or initializing a matrix of zeros to be 5 rows and 10 columns. Here is my double for loop over the 5 rows, so that corresponds to variable I, and variable j corresponds to the columns, which is the second dimension in this matrix. And then here I'm just implementing that weird looking formula that I showed in the book text. Okay, here I first just want to show you what this matrix looks like. You can see it's a floating point matrix, so the formula itself does not produce integers. And then I'm transforming this into integers just to make this look a little bit cleaner in the output. So you can see this is much easier to read than the previous version. Okay, here is the advanced method. Here I'm creating a mesh grid for I and j, and then I'm just directly implementing the formula onto these matrices instead of calculating this formula element by element. So the results are the same as you can see here versus here. Again, if you are comfortable with these more advanced matrix operations, then go for it. If you're not, then definitely stick to the double for loop here. It's totally fine. Okay, here we get to the visualization. So plt.imshow, that's pretty straightforward. Here I'm just defining the color limits. They are vmin instead of like cmin and cmax for color limits. But anyway, there's Python for you. And then let's see, here I am defining the text. So the text gets written in one element at a time. So I'm looping over, again, all the rows and looping over all the columns. And here I'm just saying that the element coordinate in the plot, coordinate j comma I is the index I comma j. Now, when you look at this code, you might think that this is backwards, right? You might think that it should be I comma j. However, this is the correct formulation, and the reason why it is correct is that the x and y coordinates of a graph are mapped onto the columns and the rows, and not the rows and the columns. So if you want to access row 3, that actually corresponds to the y-axis coordinate 3, right? So in matrices, you list the rows first and then the columns. So matrices are indexed as row column, but the plots are drawn using coordinates of x comma y. So the y-axis of a plot of an axis corresponds to the rows in a matrix, and the x-axis of a plot corresponds to the columns of a matrix. So this is a bit tricky, right? So just to repeat myself here, when you have matrices, you have the rows in the first dimension and the columns in the second dimension. But when you have a plot, you have a figure, the coordinates for the plot are given as x comma y, which corresponds to the columns and then the rows. So I know it's a little bit confusing, but that's how it works. And if you're ever confused, then this is the way to test your code. Draw something really simple, like a line between two coordinates, and make sure that that line looks good. And then you can be confident that you are indexing in the correct order. Exercise 2 is focused on giving you even more experience working with two-dimensional functions in NumPy and in Matplotlib. Start by actually getting out a piece of paper and a pen and writing down this two-variable function. So we have the sine of x1 squared plus the cosine of the square root of x2 times x1 times x2. Okay, so x1 and x2 are two variables. Sometimes in two-dimensional functions, we call the variables x and y. Sometimes tau and epsilon, whatever is the relevant variables to consider. And here I'm calling them x1 and x2. Okay, so on a piece of paper, write out this function here, and then calculate the two partial derivatives. So partial x, x1, and partial x2 for this function. Once you have that, write out three Python functions, so standard Python functions, that implement these two functions. Three functions. You have this original function and the two partial derivatives. So you're going to have three Python functions, one function for this expression here, one function for partial x and x1, and one function for partial x2. So these Python functions will take coordinates x1 and x2 as inputs and provide one value as an output, which is the output value of the function for each of these, or for the pair of x1, x2 inputs. Okay, now if you've implemented that successfully in NumPy, then you can input the following numbers and confirm that you get these results. So the function of x1 equals pi and x2 equals pi over 2, if you get a result of 1.1102, then you have correctly implemented that function, and so on for these other two functions. So this is partial x1 and partial x2. Okay, so that is just a quick check to make sure that your functions are correct. Then I want you to create results matrices. So rather than evaluating these functions for one particular pair of x1, x2 coordinates, implement them for a range of coordinates and to create an image that looks like this. So you can see that I have my domains for x1 and x2 for plotting go from 0 to 2 pi, and I set the color limits to be -3 to +3. This is the original function, this is partial x1, and this is partial x2. And then what I want you to do is create these three matrices twice. Once you create them using a double for loop and create the matrices element-wise, and then a second time create exactly the same matrices with exactly the same Python functions, but using numpy.meshgrid without using any for loops. And then the idea is that you will have 6 matrices, right? 3 that you created using the double for loop, and 3 matrices that you created using numpy.meshgrid. But these 6 matrices are really only 3 matrices because you created them redundantly. So the final part of this exercise is to compare the 2 sets of matrices from the double for loop and from meshgrid and make sure that they match exactly. So they should be exactly the same matrices, just one's created with for loops and one's created with matrix operations. Here I have the 3 Python functions that I've created for the main function, the original function, the partial derivative with respect to x1, and the partial derivative with respect to x2. And here I'm labeling this x and y, but this is what I call in the book text x1 and x2. Okay, so run that code. You can confirm that your code matches my code here. Maybe you have slightly different orders. Maybe you have the terms in a slightly different order. That's fine as long as you have the correct result overall. Here are the 2 particular values, the coordinates that I will use to confirm the accuracy of the function. Again, your function should produce the same output as this. Okay, so, and then here's where I do the, here's where I create the matrices. So I define the domain to be 0 to 2 pi for both variables. Here I'm defining the number of elements for each variable. These are the x grids that I'm going to use to create the matrix, and I'm setting both variables to be the same. Okay, let's see. So here I'm creating the 3 matrices for the function output, the derivative with respect to x1, and the derivative with respect to x2. Then I'm using underscore L here where the L is for the loop version, and that's going to allow me to differentiate and compare with the matrix version, which I'll do next. Okay, so now to create the matrices element-wise, you can see I have this double for loop over here. And for each of the matrices, the function and the partial derivatives, I am calculating the, or evaluating the function for these particular values of the x1 and x2 coordinates. All right, let's see. And then here I show the function using imshow. Nothing too fancy going on over here with the visualization code. All right, so here, you see this just reproduces what I showed in the book text. Okay, so then this code cell down here is exactly the same thing. We're creating exactly the same matrices based on the same Python functions. The only difference is that instead of using a double for loop, I am using these matrices that were created by meshgrid. If you are not so familiar with using the function meshgrid, then you can check back earlier in the text. I had a whole section about how to work with this function, how to use the inputs, and how to interpret the outputs. But I mean, one thing that's nice to see is that you can see it's 3 lines of code, I guess 4 lines of code, including the meshgrid call, no for loops, and that gives us identical output to all of this business here. Again, as I've mentioned before, written in the book and mentioned in the previous exercise, there's nothing whatsoever wrong with writing for loops and double for loops and triple for loops. If that is how you feel most comfortable with making sure that your code is accurate, then definitely go for loops. If you are comfortable working with matrix operations and vectorization, then this is more compact. It's also faster for NumPy to calculate. But all that said, the point of coding and math is not to have the fewest number of lines, the fewest characters in your code. The point is to have accurate, clean, readable, bug-free code. And however it is your style to get that to work is what you should do. Okay, so here basically, just visually, you see that these matrices look the same as these matrices. Okay, so that's great. and then to quantify the differences between them to make sure that they really are the same. There's a couple of different ways that you can calculate the differences. What I did is take the absolute value of the matrix differences, so I subtract ZL for loop from ZM for matrix or mesh grid. Then I take the absolute value of this difference matrix, because we don't care about which one is positive or negative, we just care about if they are different. And then I sum over all of those elements. And of course, the idea is that if these two results matrices are identical, then the sum of the absolute value of their differences will be 0, of course. And that's what we see in all these cases. Now, just one small word, if you are doing this in practice for other matrices or more intensive calculations, it is possible that you will see some numerical differences here, but they may be very, very small, on the order of the machine precision error. So these are, really 0. But if you get values that are, 10 to the minus 14, 10 to the minus 16, somewhere around there, those are zeros plus rounding errors, and you can still be confident that your code is correct. Now for exercise 3 of chapter 10. Now, most of the time when I visualize two-dimensional images or two-dimensional matrices as images, I use flat images with color coding to indicate the matrix numerical values. And that's basically what I recommend most of the time. The flat images are maybe not quite as beautiful to look at, but they do convey information in a better, clearer, and more readily accessible manner. That said, interactive 3D renderings of functions can be really fun and beautiful, and you can do that with the Plotly library in Python. So so the purpose of this exercise is basically just to introduce you to Plotly and make sure that you get at least the basic idea of creating graphics in Plotly. So you import the library as using this code. So import plotly.graph_objects, and it's often abbreviated as Go. So graph objects in Plotly. Okay, so then what you want to do is implement these three functions here. So the sine of x plus y squared, and then here's function b for panel b, and here is c. Now c is an interesting function because it has a lot of parameters involved in it. So it is a function of two variables, x and y, but this function takes a number of other parameters, such as f, which corresponds to the spatial frequency, u, which is a rotation matrix, and sigma, which defines the width of this Gaussian little hatch over here. So if you want to reproduce this result visually exactly, you can use these parameters here. And of course, once you have implemented the code, you can start playing around and see what other values for these parameters you find to be particularly interesting. Okay, so then these three functions here will create these three images in Plotly. And then just out of depressing curiosity, I recreated this function here, function b, using a flat map with just grayscale. And I think you agree that this is way, way more interesting to look at in Plotly than this flat map in Matplotlib. Nonetheless, unfortunately, this one is more informative than this one in terms of reading out the particular values. All right, so here, this is literally just the code that I showed in the book text. Here I define the function using the output matrices of MeshGrid, and you can see that the basic layouts, the basic function call of a three-dimensional interactive Plotly visualization is really simple. So we can just say go.figure, and then we say the data equals, and in this case, it's literally just go.surface, x coordinates, the y coordinates, and the z coordinates correspond to the function values that you see here. Okay, and then I'm just specifying the size of the of the figure. And that's it. Then we run it. And then you get this neat result. Let me zoom out a little bit here. So here you see the function, and now I can left click and drag. So I'm holding down the left mouse button and dragging this around to view it from different angles. You can scroll to zoom. You can hold down, I think it's shift. No, maybe it's command. Alt. Okay. Yeah, you can hold down control and then click and drag, and that moves it around like this. Plotly is a really cool library for advanced visualization. I don't discuss Plotly anymore in the book other than this basic visualization. If you are into this, if you want to learn more and gain more skills with using Plotly, then that's great. I fully support that. But I don't, that's outside the context of this book. Okay, let me see. Yeah, this is for the next function in panel B. And this also looks really cool. This would make a great salad bowl, I think. If you could put some like legs on it so it would stand, then you could put a salad in here, or maybe like it's a dish full of M&Ms or something like that. Okay, yeah, and then this is the code that shows the boring representation of exactly the same function as this. So I think you agree that this looks really, really nice, and this is a lot more fun to interact with. You can't really interact with this one a whole lot. There are two goals to exercise 4. Both involve using SymPy to work with multivariable functions and their derivatives. So the first part of exercise 4 is to calculate the first order and second order partial derivatives of a multivariable function. So you see that function here. That is x times e to the power of minus x squared minus y squared. So this is your base function that you start working with. Implement this function as a symbolic expression in SymPy using symbolic variables. And then you want to calculate, again in SymPy, the first order partial derivatives, so partial x and partial y, those you see printed out here. And then we have the 4 second order partial derivatives of the partial x, y, y, and the 2 cross terms over here. You can also visually confirm that these two, so the two orders of the second order partial derivatives are equal to each other. Remember this I discussed earlier in the book. This is given by Clairaut's theorem and is fairly straightforward to prove. Okay, so basically producing this output here is the first part of exercise 4. Once you have that, then I would like you to create this figure here by using sim.plotting.plot3 to generate 3D surfaces of the function that you see here, the partial derivatives, and the higher order, the second order partial derivatives in the second row here. Of course, we don't need a separate visualization for f, y, x, because we know that that's going to be exactly the same plot as this one here, so f, x, y. This is a great exercise for making sure that you really understand how to use sim.diff, this function for differentiation. Okay, anyway, here I create the two symbolic variables. Here I write out the formula. So x times e to the, now I wrote this out as minus the quantity x squared plus y squared. But then SymPy actually prints it out as minus x squared minus y squared. It's just a visualization. Okay, here I calculate the first order partial derivatives. Here are the second order partial derivatives, and you can see that the code is the same as for differentiating for one variable, or the first order derivative. I'm just taking the derivative of the derivative. So f underscore x is the variable corresponding to the derivative of the function with respect to x. And then I'm taking the derivative of the derivative, again with respect to x, or here I'm differentiating with respect to y. All of these lines of code here are just printing out the results, and you can see, basically you write this line of code once, and then you keep copy pasting, and you just have to be mindful of changing all the text and the variable names that need to be changed. Otherwise, this part is fairly straightforward. Here is where I'm creating the visualization. So here I'm using sim.plotting.plot3, input the function, and the domain and the two domains for the two input variables. And then here I'm specifying the title. Here I write show equals false, and that's because I don't want to plot each of these six figures or each of these six visualizations in its own figure. Instead, I want to just create variables that represent those visual objects, those axis objects. And then I use this function sim.plotting.plotGrid to create a 2x3 grid. And here are all of the plot objects that go into that grid. Okay, and then here I'm specifying the size for the figure. Now, if you want another way to do this, if you don't create all of these variables, you could just expand this line of code here so that instead of each of these variables, you have a direct call to sim.plotting.plot3. Several ways to implement this correctly. As I mentioned multiple times before, visualization with SymPy is something that it's good to be familiar with the basic plotting in SymPy so that you can make some visualizations quickly. But when you want to make really high quality graphics, it's almost always better to get the data from SymPy into NumPy using functions or list comprehension, and then visualize with Matplotlib or maybe with PyPlot, as you learned in the previous exercise. Okay, so here we go. Here we see the function. I'll zoom out a little bit. And yeah, I mean, you can see the arrangement is not very nice. There's some overlap here, and it's not so clear that the title here really corresponds to this plot and so on. Anyway, these are issues that you would fix in Matplotlib much easier than what you can do in SymPy plotting. Here we are with exercise 5 of chapter 10. Now, so far in this chapter, we have calculated partial derivatives of multivariable functions in two ways. One is by hand, and two is using SymPy. So both of those are analytic methods. But in previous chapters, you learned how to differentiate empirically, numerically, by calculating differences between successive evaluated function points and then dividing by or scaling by delta x. Okay, so that's what you want to do in this exercise. Basically, it's going to be to reproduce exercise 2, but instead of calculating the derivative on your own, empirically or analytically, or in SymPy, you want to do it numerically as an approximation in NumPy. Okay, so here is the function that you want to implement. Now, you don't implement this as a symbolic expression. Instead, you evaluate this function numerically in NumPy, and then create the first order partial derivatives in NumPy using h equals 0.01. Okay, so I will first scroll up and show you what your result should look like. And then I will scroll up and show you the equations that you implement in NumPy. So here we see the figure from exercise 2. And this is the function, and this is the partial derivative with respect to x1 and the partial derivative with respect to x2. And these are the three images that you will create empirically in NumPy. And here we have the two functions, the two formulas for the partial derivatives of f of a function with respect to x and with respect to y. And again, I discussed this at length in the book text, but the idea is that this is exactly the same as the limits-based definition of derivatives that I introduced earlier in the book with single variable functions. The only difference is that you have a function of two variables instead of just one variable. So here you are only manipulating x, and here you are only manipulating y. And now, of course, in like pure math, for analytic differentiation, we consider what happens as the limit of h goes to 0. But here in this function, in this exercise, because we are estimating these derivatives in NumPy, we set h to be some fixed value. And I recommend starting with 0.01, see what that looks like. Once you have the code and you can reproduce the figure correctly, then you can start exploring different values of h, like maybe h equals 1, or h equals 0.0000000001, something like that. By the way, some of the variables and functions that I use for this exercise were created for exercise 10.2. So you might need to, if you start getting weird results or if you run into error messages, you might need to go back and just rerun the code for exercise 2 to make sure that those variables are correctly stored in Python's memory buffer. Okay, so here I define h to be 0.01. I will change that in a little bit. And here I get the x and y matrices for evaluating the function. Now, I actually called these x1 and x2 in the book text. Okay, here is the function from before, and here's where I'm creating the partial derivative. So I'm using numpy.diff. You have seen this function quite a few times before. But the difference between how we've used it before for single variable functions versus how I'm using it now for matrix input is that we need to specify explicitly the axis along which we are computing the numerical differences. So here for x, for partial x or x1, we need to differentiate or get the calculate the numerical differences across the second axis, and that's because we want to know how x is changing for each specific value of y. And now here we are investigating how y is changing, or variable x2, whatever you want to call it, for each specific value of x. And then, of course, with single variable functions, we divide by delta x or dx, and here we are dividing by h, just calling the same variable, same quantity, a different variable name. Okay, very good. And then here is where I create the figure using IAmShow, nothing too tricky in that part over here. All right, and here we get the matrices. Certainly, visually, they look basically the same as what we created using the analytic calculations of the partial derivatives. So that's pretty cool to see, basically, that the numerical approximation to the derivative looks the same, gives, visually the same appearance as the analytic solution. Okay, so that's very nice. And now I want to try changing h. So basically, I'm just approximating the derivative with a coarser resolution for the calculation. And then you can see that, overall it looks the same, but it's grainier, right? And here you see it looks very pixelated compared to the image before. This is very similar or exactly the same concept as what you learned for single variable functions with regards to the resolution and the accuracy of differentiation. Now we can make this a little bit more extreme and set h to be 1. And let's see how this looks. And here it comes. Okay, now it doesn't, numerically, this is still more or less an accurate approximation, but the resolution is so coarse that you cannot make out any of the details of the functions and the derivatives anymore. So this is clearly a case where, this is just too coarse. The resolution is too coarse. Now, you can make this finer. In theory, if you would have an infinite number of zeros in here, this is going to be the true derivative. Now, this is just wild. We couldn't actually do this in Python. The issue here is more about computation time. If you set the resolution to be really, really, really fine, you might think that that is good because we get a more accurate approximation of the derivative, of the analytic derivative. And that is true. This resolution is more accurate than this resolution, but the matrices start to get really, really large. the computation time is going to increase by a lot, and it's not necessarily clear that there's a real advantage to having hyper good resolution compared to just pretty good resolution. This is a determination that you will need to make in your applications. Welcome to exercise 6. The goal of this exercise is to evaluate limits of two-dimensional functions or two-variable functions using SymPy. So there's two parts to this exercise. One part is about working with SymPy and NumPy and Matplotlib to visualize a two-variable function. And then in the second part, we will calculate some limits and see how SymPy deals with limits of two-variable functions. Okay, so start by implementing this function here as a symbolic expression. So put this function into SymPy. And then what you want to do is calculate the two partial derivatives, so the two first-order derivatives in SymPy, and then convert these into lambda expressions using sim.lambdify, and then evaluate the functions in NumPy and visualize in Matplotlib. These are pretty neat looking functions here. Here's the main function. This is the partial derivative with respect to x and the partial derivative with respect to y. And then I've also printed out the actual functions for the partial derivatives in the panel titles up here. Okay, now when you look at the formula, it's pretty plain to see that we're going to run into problems at the origin of this graph, so at 0, 0. And that is because when x and y both equal 0, we have something divided by 0. In fact, it actually ends up being 1 divided by 0, but the numerator doesn't matter because we still have problems with this denominator. But we can ask the question, what is the limit of this function as we approach the origin? Okay, and that is what you are going to solve in the next part of the exercise. So use sim.limit to calculate and print out the limit at two xy coordinates, as I show in this screenshot here. So the limit as we approach x equals 1 is a function of y. Now, remember from earlier in the chapter, I discussed limits of two variable functions, and what I said was that when you compute the limit as we approach from one variable, the resulting limit can actually be a function of the other variable. It's not always going to be a function. It's possible that y just kind of drops out or there is no y here. But very, very often you're going to find that the limit of a two-variable function as you approach the numerical value on one variable is going to be a function of the other variable and not a single number, as we saw for limits of single variable functions. And why that is the case and how you interpret that and how to work with that, this I discussed in more detail in the text. But basically the idea is that you calculate the limit twice. So you calculate the limit as you approach one variable or one value for one variable, and then you take that result and you plug that into another limit for another variable. Okay, so we're going to compute the limit of this function as x approaches 1. If you have implemented the limit problem correctly in SymPy, you should produce this output. The limit as y approaches pi, and this should be the output here. So here we get a function of x. And then we take the limit as x comma y approaches 1 comma pi. Again, you have to make sure that you are implementing this expression correctly in SymPy. And you should get a result of somewhere around minus 0.0469. That's the numerical approximation. You can see this is no longer a function of x or y. This is just one number because we are evaluating the limit at a point, now defined by two variables. Okay, and then finally repeat this, but for the limit as x and y go to the origin of the graph, and here you should get a result of 1. Okay, and then, this result also is consistent with the graph here that the colors get lighter. I don't have a color bar here, but the colors are getting brighter towards the origin. And yeah, so the limit here is plausibly equal to 1. Here I define the two symbolic variables. Here is where I define the function. Now, I have mentioned earlier, I think this might have been in chapter 2 or chapter 3, that when you have complicated looking functions with lots of terms in them, it is very often useful, not necessary, but it's useful, it's helpful, if you can break up the function into multiple lines of code. And that's what I do here. So I have a separate line of code and a separate variable for the numerator and for the denominator. And then here I just express the fraction. This makes your code easier for you to read, easier for other people to read, less likely to make errors. And if there are errors, those errors will be easier to spot. Okay, and then this is just, confirmation that I've implemented the function correctly in the code. Okay, here I lambdify the function itself and the derivative of the function, the two first-order derivatives. And I'll run that code. And then here is where I evaluate the function and its derivatives for specific values of x between -10 and +10. And here I have some IMShow functions to basically just to visualize the three maps as I showed in the book text. Now, in the book text, the figure that I showed in the book text did not have this funny little white pixel here in the center. So why do I have that little white dot in the center? It is related to this warning message here, and that in turn is related to this grid resolution here. Now, I'm not going to answer the question because I've had lengthy discussions about this issue in the text in earlier chapters and also in videos for exercises in earlier chapters. So I will leave this as an exercise left to the viewer, okay? Here is where I calculate the limits. So here I take the limit as x approaches 1, and now I'm just writing out the sim.limit of this function, and we are just interested in this variable x at a value of 1, so as x approaches 1. And then I take this SymPy output, convert that into LaTeX code, and then put that into the display math function pair. And yeah, that's going to give us the limits. Okay, then here, just showing how to calculate the two-dimensional limits. So these two lines of code here correspond to this piece of output over here. So here's where I'm calculating the limit as x goes to 1 and as y goes to pi. So the way that I do that here is writing sim.limit with the function and then the variable and the limit value. And now what you could do is make this be an output and say lim 2d xy, let's call this 2, equals sim.limit and then input this lim 2d xy. Now this is perfectly fine. Here I'm calculating the limit twice. There's nothing wrong with this code. It's great. But here I'm just showing you in my solution that you can also use limit as a method on a symbolic object. Okay, so the output of this function before it gets assigned to this variable, this is an object, and then I apply this method to the method limit to the output of this function. And now because this is a method on an object, we do not need to specify the object that we are working on, right? Because it's obvious that this limit will be calculated on whatever comes before the dot here, which is the expression output of sim.limit. I hope that makes sense. It's probably easier to look at this and understand it than it is to listen to me try to explain it. Okay, now I didn't explicitly show both of these lines in the book, but this is just to demonstrate that the limit for this example is the same regardless of the order in which you calculate the limit. That is, of course, not guaranteed to occur. It is possible that the limit is different depending on whether you calculate the limit coming from x first or from y first or any other direction that you're coming from. But in this case, the limits are symmetric. Welcome to exercise 7 of chapter 10. In this exercise, we are going to explore how to create gradient fields and also visualize them and calculate their magnitudes manually by using NumPy instead of by calculating them analytically in SymPy. So let me show you the first figure that we are going to create in this exercise. Here you see the figure. So there's two panels. You can see that the background image, which is this contour of this kind of like nice looking smooth pattern, that's the same in panel A and panel B. You can also see that there are these arrows representing the gradient of the partial derivatives in both of these images. The key distinction between panel A and panel B is that in panel A, the gradients are visualized with magnitude. So the length of the arrow corresponds to the magnitude of the gradient, or the collective sizes of partial x and partial y. Okay, and then here the gradient magnitudes are normalized. So you see that every arrow has the same length and the same size arrowhead. Still, the directions are always pointing toward, or the arrows are always pointing in the direction of larger values in the image in this two-dimensional function. Okay, so how do we create this? Well, for starters, here is the equation that we are going to plot. So it's x times e to the power of minus x squared plus y squared. Now, this exponential term on its own creates a two-dimensional Gaussian, so like a Gaussian blur. And then we multiply it by x, and that is what gives us this sign pattern here. So we have negative numbers to the left and positive numbers to the right. Okay, so that's how you create the function. And then what I want you to do to create the gradient is to use NumPy and Matplotlib, of course, for visualization. So you're not going to use SymPy the way that I showed how to use SymPy to create exactly this figure earlier in the text. Okay, so there's more to do in this exercise. There's more parts, but I want to switch to Python and show you the code to generate this figure, and then I'll come back to the book text and explain the rest of the exercise. Here I am evaluating the function using these matrices of x and y values that I have obtained from MeshGrid based on these x values and also y values. You can see it's going to be a square isotropic map here. Now notice also that the n is fairly low, right? Very often in this book, we are simulating equations. We are numerically evaluating equations using, hundreds or sometimes thousands of points. Now, you can do that technically for plotting gradients, but the problem is that the arrows are going to be so dense as to be basically pointless. You won't be able to see anything. So if you are plotting arrows on top of a function, it's best to use a relatively coarse grid so that the visualization is more interpretable. Okay, here you can see I'm using the numpy.gradient function. We will use this function a couple of more times throughout the book. And if you provide a two-dimensional input into the function, which is the two-dimensional function output map, z, then the output is also going to be two matrices for gradient x and gradient y. So this is the partial derivative along direction x, and this is the partial derivative along y. Here is where I calculate the magnitude of each element in these matrices, grad x and grad y. So how do we get the magnitude? Well, what we want to know conceptually, as I discussed earlier in the chapter, is the length of the line at each gradient location. And how do we get that length from the local origin? Well, it's we just use Euclidean distance. So it's the x part squared plus the y part squared, and then we take the square root of that. So that is the length of the gradient vector at each point that we are estimating in z for the gradient of z. And then, so once we know the magnitude at each for each gradient, then to normalize the gradient lengths, all we need to do is divide by the magnitude. So basically, this ensures that the magnitudes or the directional arrows now have a magnitude of 1. They all have a length of 1. Okay, and that is what we see in this plot here. So I'm using the quiver function, which plots the arrows. And then you can see, yeah, this is, both of these come from exactly the same function, exactly the same gradients. The only difference is that this is like the raw gradients, and here, this is where I've normalized by dividing by the magnitude. And again, the magnitude is calculated using Euclidean distance. Now for the next part of this exercise. That is to visualize the magnitudes of the gradients before and after the normalization. So I just showed you how to calculate the magnitudes, and that you see here. And then here is the normalized magnitudes. And as I write here in the text, it's all white. You might be concerned that this is a bug in the code. It's not visualizing anything. In fact, it really is showing the normalized magnitude, but the normalized magnitudes, by definition, are all equal to 1. So the fact that this map is white everywhere is actually a good thing. This confirms that we've done the right calculation because all of the magnitudes are equal to 1, which is exactly how they should be. These magnitudes here in panel A, these are the raw magnitudes, and these are not all the same. It reminded me of a pig snout. It's like, imagine a pig pressing its nose up against a dirty windshield or something. I don't know. So what you can see is that it does make this kind of like figure 8 pig snout shape. And what does that correspond to? Well, that corresponds to the lengths of these arrows here, these directional arrows. So out here, basically the function is changing very little over space, right? So if you would just take a slice, just cut a line, cut a section out of this map, it would look very flat. The gradient is very small all around here in these parts where the image is gray. So that means that the gradient or the two-dimensional derivative is very small. The function is not changing. In contrast, here you get to these peaks here and here. So this is a big peak. This is a big valley here. And the function is changing very quickly. If you would draw a line, take a line through one of these values here, you would see that the function changes very quickly. The line becomes very steep. So therefore, the gradient or the two-dimensional derivative is very large. So these arrows are longer. That's represented in the magnitude of the gradient. Okay, and that is what we see here. So here I have I call this the raw magnitude. This is, in fact, exactly the same piece of math that I have calculated in the previous cell. Here I called it magnitude. There I'm calling it raw magnitude. I guess I could have called it raw magnitude up here, but I just wanted to rewrite this variable and repeat this calculation so that you can see the raw magnitude and the normalized magnitude very close to each other in 2 lines of code. Okay, so yeah, that is the Euclidean distance. Here we have exactly the same code, but now I'm dividing by the magnitude for each of these partial derivatives matrices. Okay, and now we can just look at the numbers. Actually, let me first, I'll first draw these and then we'll look at the numbers. Ignore the numbers for the moment. Okay, here, this is just drawing what I showed in the book text. I'm not sure how that error creeped in here, but anyway. Okay, there we see, yeah, here is the 2 functions or the figure that I showed in the book text. Okay, and here, just to look at the numbers, here we see the raw magnitude has a lot of different kinds of numbers, right? So the numbers are, they take on lots of different values. In contrast, if we would just look at the normalized magnitudes, here you see that they're all ones. Every single pixel in this image is 1, and that is not surprising. That is exactly how we created this magnitude in the first place. Exercise 8 of Chapter 10 is focused on gradient descent, and in particular, expanding gradient descent from 1 variable, which you learned about in Chapter 6, to 2 variables. So if you like, you can copy the code from exercise 6 dot question mark question mark. This is just unresolved crosslink in LaTeX because I didn't compile that chapter. Anyway, you can figure out which exercise it comes from. Or if you like, you can use the description from this chapter and recode gradient descent from scratch and now for 2 dimensions. If you are copying gradient descent from a single variable code from chapter 6, it's actually not that much more work here. It's really only changing a couple of lines of code. In fact, if you are comfortable with gradient descent for one variable, then honestly, the hardest part of this exercise is just getting this ridiculously long formula into SciPy without making any mistakes. So in fact, that's what you want to do. That's the first part of this exercise. Translate this expression, this function of 2 variables, x and y, into SymPy. And then you can have SymPy calculate the partial derivatives, so partial x and partial y, and then visualize these 3 functional maps that you see here. So this is the function, this is the partial derivative with respect to x, and the partial derivative with respect to y. Now, what we are going to do in gradient descent is drop our little, pin somewhere in here, estimate the minimum starting off, at random or picking one particular starting location, and then using the gradient descent algorithm to find the minimum, which in this image corresponds to the darker pixels. So this is the global minimum. Ideally, we would want to end up with a marker here, regardless of where we started from. Okay, you will get to explore. You can explore a bit in this exercise, but you will have an opportunity to explore in a later exercise. How the final result depends on the starting location. So for example, if you start here, you're not going to get all the way down here. You're going to end up stuck in a local minimum over here. Okay, I don't want to go too much into that now because you will do that later. Okay, so I'm going to first start by showing you the code to get this far, and then I will come back to the book text and walk you through the rest of the exercise. Here I'm creating 2 symbolic variables, and here is the math function distributed over 3 different lines of code. Okay, so this is not terribly hard in the sense of like conceptual calculus knowledge, but you do need to be pretty careful that you are writing out the function correctly. Okay, and then we create 3 lambda functions for the original function, which is what I've written here, and then the derivative with respect to x, and the derivative with respect to y. So I'll run that code, and from here, the rest of this is not so difficult. Here I'm numerically evaluating the function and its 2 partial derivatives, and then I'm using the imShow function to visualize those 3 matrices exactly how you see in the book text. Now for gradient descent. So you want to implement gradient descent as I described in chapter 6 for single variable functions, and again in this chapter for multivariable functions. In this case, I would like you to start, instead of picking a random starting location, start at this xy coordinate. So x equals minus 0.4 and y equals 1. And the training parameters are eta. Remember, this is a learning rate that basically slows down learning, so it multiplies the gradient, and 1,000 updates or 1,000 iterations through our for loop. And if you use these starting parameters and learning parameters, and if you've implemented the function correctly, then you should find exactly this result. Okay, so you should get that gradient descent identify the minimum as 0.23 and minus 1.63. Okay, I will show you where that is on the map in a moment. The final part of this exercise is to then modify the code, or just add this in the first place, so that the estimates at each location, or each iteration in the for loop, so each run of each update from gradient descent, are stored in a matrix. Okay, so it's going to be a 1,000 by 2 matrix. So there are 1,000 iterations, so 1,000 updates of the learning algorithm, and then we have the x and y coordinates. Now, once you have that matrix of coordinates as a function of training, then you can actually visualize the trajectory of the algorithm here. Right, so here is where we started. You can see this is minus zero point 0.4 and minus 1. This was the starting location, and then gradient descent managed to find this location here as being the minimum of this function. So that is great. This is a highly super duper successful demonstration of two variable gradient descent. Here I specify the starting location to be minus zero point 0.4 and minus 1. Again, for this exercise, I recommend using this exact starting coordinate so you can reproduce my results. And in the next exercise, I will encourage you to explore different values. Okay, here's the training parameters, and here is the loop that implements gradient descent. Now, you can see that this is nearly identical to the gradient descent algorithm for a single variable. The only difference is that in the single variable case, this variable grad here was just one number, one value corresponding to the derivative of the function at the current estimate of the point, which is called local min. Here we have a NumPy array of two elements here. So this is partial x and this is partial y, always of the same coordinate evaluated this function. Okay, and then this is, one of the single most important expressions in modern computer science, which is we update the local min according to itself minus the gradient times the learning rate. Okay, and then here is an extra little bit of code that I'm using to store the location. So store the XY location at this element of training. Okay, let's see. Here it runs through. It's very fast, of course. Here we get the final location, and now I'm just going to plot the image, the original image, the peaks function, and then the trajectory for x and y. And I'm drawing this as a white line. Yeah, and here is just some markers at the start and at the end. Exercise 9 is open-ended. There is no specific, narrow, concrete goal for you to achieve in this exercise. Instead, what I want you to do is explore the code for gradient descent and just take some time to think about the algorithm in a little bit more detail after having worked through the previous exercise. Gradient descent is a simple algorithm, and yet it is one of the single most important algorithms in modern humanity. It is the optimization algorithm that powers basically all of deep learning, artificial neural networks, including computer vision models, language generation models like ChatGPT and Gemini and Claude. Basically, nowadays, where there is a need for nonlinear optimization in computer science and in machine learning, you will often see gradient descent at the heart of those systems. Okay, so yeah, I give a couple of suggestions for starting to explore, basically trying different start points on the map. And a question, does gradient descent always work? Okay, there's actually, that is an open question. It's an ambiguous question. You can interpret this question in several different ways, and I'll give a couple of different answers. All right, so here we saw in the previous exercise that when we begin at this location, gradient descent was really super duper a lot successful, and it got to exactly the minimum point of this two-dimensional function. That worked great. Okay, and then my suggestion is, let me see, I have to start up here. So my suggestion after that was to start at 0, 1.8. Okay, like this. So now I'm going to rerun this code and have a look at the trajectory here. So we started here at this peak, and now looking at the function, it's pretty clear what should happen. The result should be that we go down this way. This would be the ideal result that we ended up here. But maybe, at least if gradient descent went over to this side, then we would end up at a local minimum. Here, we just went completely off the charts, outside of the range of the function. Now, why did that happen? Well, This looks uniformly white, but in fact, this is not uniformly the same value. This is just a color saturation. In fact, maybe I will undo the colors here. Let me just get rid of these two bits here. Okay, let's see if we can see a little bit more gradient here. Okay, yeah, so here we see more color gradient, and that allows us to interpret the gradient descent a little bit better. So it looks like, by my eye, the absolute peak of this function is somewhere around here. And we started just a little bit north of that peak. So in fact, gradient descent did what's the right thing from the perspective of the algorithm, which is to move towards more negative values, which happen to be straight up or straight north in this function, just because it happened to start a little tiny bit north of the peak here. Okay, now we know we have, the bird's eye view of this landscape, of this two-dimensional function. So we know that the right thing to do is actually to come around this way. But that's not what it did, because gradient descent does not understand the entire landscape. It doesn't have access to the full gradient, the full derivative map, or the full function map. All it knows is the local step. So it just knows that if I go in this direction, then that's the wrong direction. That's going up towards up the function. And if I go in this direction, then that is the correct direction. Now, if you take a course or read a book on machine learning, optimization, deep learning, you will learn various tricks that people use to avoid or at least minimize the risk of situations like this. But nonetheless, this is a very possible outcome of gradient descent. This is something that can happen with this algorithm. Okay, and then, what I would like you to do is continue to change this starting location. You can pick points at random. You can pick points based on just looking at the plot. For example, let's see, if you start here at this cusp around here, is it going to go towards the local minimum or towards this local minimum or the global minimum over here? Lots of interesting things you can explore. The next question in the exercise here was, does gradient descent always work? Now, there are several ways you can interpret this question. One is from a purely mathematical interpretation. Does gradient descent algorithm always work? And there the answer is mostly yes. You need to have a couple of assumptions, like the gradient or the function needs to be numeric. It needs to be differentiable. So the function itself needs to have well-defined derivatives, not necessarily everywhere, but it needs to have a well-defined derivative in whatever is the search space that you want to consider. So for example, taking this two-dimensional function, let's say there were some discontinuities and the derivative is undefined, but it's all the way out here. That's totally fine. It doesn't matter. As long as we are constraining the algorithm to operate within the domain in which we have continuity and differentiability. Okay, so that is one way, one interpretation of the question, does gradient descent always work? And then for practical purposes and applications, the way to interpret that question is whether gradient descent will always give us the answer that we are looking for. Now, these one-dimensional and two-dimensional cases are interesting case studies for understanding the dynamics and behavior and limitations of gradient descent. Because here you can see the answer to this question is no. Gradient descent does not always work in the sense that we are not guaranteed to arrive at the global optimal solution or even, really a kind of acceptably local solution. And that is because of the parameters that go into the procedure. That's because of issues like we identified here. So now let me go just to show you another example of how gradient descent can not work very well. Let me show you, again, this is going back to what we solved in the previous exercise. Okay, so this worked great. What I'm going to do now is decrease the learning rate. And that's all I've done. I've changed the learning rate from 0.01 to 0.001, kept everything else the same. And now, now it still looked pretty good. Okay, let me set the learning rate even lower. Basically, what I want to show you is that when the learning rate is too small, then it's not moving fast enough. It still is actually getting there. Let me drop the number of training epochs just to, here we go. So we have too few training iterations, and the learning rate is very small. And so here, yeah, we get kind of a nonsense result, which is moving in the right direction, but it's certainly not the result that we would look for. There's other things you can do. You can make the learning rate too high, and you can see that is also going to have a wild effect. So we started off here, and we ended up all the way out here, okay, even though we should be here. So if the learning rate is either too high or too small, then we can also get unstable or incomplete results. So there's many, many ways that the gradient descent algorithm can continue to work mathematically, but not work in a practical sense of giving satisfactory results. Again, in a course on machine learning or deep learning, these are the kinds of issues that you would study, and you would learn how people have addressed these kinds of problems. This will be a short video because this exercise is simple. Modify the code from exercise 8 to perform gradient ascent instead of gradient descent. Okay, this is really as simple as you probably think it will be. It's just a nice little exercise just to make sure you are understanding how all the moving parts of gradient descent fit together. Here we are looking at the code for exercise 8. Now, there's basically just two ways that you can transform gradient descent into gradient ascent. Well, actually, maybe there's a couple of ways. Okay, let me go back. One way, so I'm going to discuss three ways. One way is to just flip the sign of the function. So if you would take this entire function and make the whole function times -1, right? So you're just flipping the sign of the entire function, and then you're still performing gradient descent, but now, you're looking for peaks in the function instead of dips. Okay, but that is generally not a recommended approach. Sometimes that can be appropriate, but very often you also want to know the real original nature of the function. So flipping the function itself is not always the right thing to do. Okay, so therefore that leads me to point 2, or option 2, which is to change the sign of the learning rate. So it's kind of like we're learning backwards, or we're learning in reverse. And another option, which is probably the preferred option in most cases, is to flip this sign here. So instead of subtracting the gradient or the derivative, we are adding the derivative. So that means instead of moving in the direction of function smaller values of the function, we are moving in the direction of larger values of the function. Okay, and then I will just show you what this looks like. This is for gradient descent from exercise 8. And now I've run the code for gradient ascent. The starting location is the same. And here you can see we finished at this light patch over here. So instead of going towards more negative values of the function, we've climbed up towards more positive values of the function. Here we are with exercise 11 of chapter 10. This is a fairly long and multi-step exercise, and if you are unfamiliar with linear algebra, then there are going to be some new concepts, like the determinant of a matrix. But I would like you to focus more on the description, the multivariate calculus aspects of the exercise, and don't worry too much about the linear algebra concepts, like how to interpret a determinant. Okay, so anyway, in this exercise, we will explore the Hessian matrix of a two-dimensional or two-variable function. The Hessian matrix is something I introduced earlier in the chapter. It's basically a way of organizing the second-order derivatives of a multivariable function into a matrix. So it's a very compact representation of second-order derivatives. It's used in image processing and in some advanced optimization methods. And it's a little bit analogous to the second derivative of a single variable function. And so therefore it's used to quantify curvature and inflection points in 2D landscapes. Okay, anyway, let me go through the first couple of parts here in the text, and then I will show you the solutions in Python, and then I'll come back to the text and explain more of the exercise. So your first goal is to implement this wacky looking two variable function here in SymPy. We want this in SymPy because we are going to like differentiate it and do other symbolic operations on it. Okay, so here is what that function looks like. Now, what this means, where it comes from, I don't know. I just kind of made it up as I went along. Okay, so that's step one. Step two is to determine the domain of this function. Now, the domain of a two-variable function actually has two variables in it. So you need to think about the domain of x and the domain of y. And then third, you want to calculate the first and second order partial derivatives in SymPy, using SymPy, and then visualize them as in the figure on the next page. And I visualize using a domain of 0.1 to pi. Okay, so here we have the function, the partial derivative with respect to x, partial y, and here is the second order partial derivative with respect to x and x. This is the second order derivative on y and y, and these are the mixed partial derivatives for fxy and fyx. Now, because this function is continuous and differentiable at all, not everywhere in the function, I'll talk about that in a minute when I talk about the domain. So it's not continuous everywhere, but this function is continuous and differentiable at all of the points at which I am evaluating the function, which is 0.1 to pi on both the x and y variables. Therefore, Claro's theorem holds in this restricted domain, and the two mixed partial derivative orders are equal to each other. Okay, so there's more to this exercise, but let's take a moment here to work through this so far, and then I'll come back to it. Okay, so let me first discuss the domain of this. So let's first just think about x. Now, x can be any variable. Here, x can be any real valued number, I mean. Here, it can be any real valued number. Now here, this is tricky because x, it's under the square root. So you might think that x needs to be strictly non-negative. So it could be 0 or positive. But think about what happens when y is also a negative number. So in fact, x could be negative. It could take on negative values only if y is also taking on negative values. And then you would have two negative numbers here, and that would give us a positive square root. Okay, so now let's think about y. Here, in principle, inside the logarithm function, we can only have positive numbers, but because we are raising y to the power of 4, negative values of y are also permissible, except not 0. So we cannot have y equals 0, but y can be any other number, positive or negative. Now here we have, of course, the same situation as x. So y could be negative, but only if x is also negative. So you can see that the domain of this function has an interaction between x and y. I have written that out for you here. So the domain is x and y in R2. So these are real numbers. It's R2 because we're considering this to be like a tuple, like a two-dimensional number. Such that x times y, so the product of x and y, must be greater than or equal to 0, and y cannot be 0. Y cannot equal 0. Now that is the strict domain, which means that, yeah, as I mentioned, x and y can both be negative, but, you know, just to keep things a bit simple, in the rest of this exercise, I've only used positive numbers. Okay, here I'm implementing the formula. Here I calculate the first derivatives and the second order partial derivatives. Okay, and in this case, you know, the function might be like weird, but there's nothing particularly difficult about it in terms of differentiating. Of course, if you like, you can differentiate this function by hand. You certainly know enough to be able to do that. It's a little bit tricky because you have to use the chain rule and the product rule. But yeah, and actually also here you need to use the product rule. But otherwise, it's not terribly sophisticated. You just have to be mindful of working through all of the differentiation rules. Okay, here I'm creating the uh, grid to evaluate the function on. So 0.01 to pi. And actually, this looks like a tiny little divergence from in the book text. I wrote zero point 0.1, and here it's 0.01. I will fix one of those, and then yeah, the rest of it is just lambdifying the functions and the derivatives, and then evaluating them at these x-y axis grids. Okay, and that's how we get all of these images that you see here. Very good. Now for the fourth and fifth parts of this exercise, and then I'll show you the code again, and then I'll come back and explain the sixth and final part of this exercise. So create the Hessian of this matrix as a matrix object in SymPy. Now, previously or so far in the book, I haven't discussed matrix objects in SymPy, but it's essentially just another symbolic representation of a bunch of symbolic expressions. So otherwise, there's nothing particularly new or fancy about this. And so the idea is to have this Hessian matrix in SymPy with functions in each of these elements. And what are these functions? Well, of course, they are the second order partial derivatives. Now, these are all functions of x and y that you are going to use to create the SymPy matrix object. But then what I want you to do is use the substitution method, as you already know how to do for everything else in SymPy, and find the matrix for h of 1 comma 2. So what does this mean? This means that this is the partial of x, the second order derivative with respect to x and x. Here's the second order derivative with respect to y and y. And these are the cross terms over here. And then we substitute 1 for x and 2 for y. And then we can evaluate that matrix and get something that looks like this. Of course, this is a symbolic representation, and you already know how to evaluate this to get actual numbers. Okay, so that is part 4. And then part 5 of this exercise is to look into this thing called the determinant of a matrix. The determinant is a number that's calculated from all the matrix elements. Yeah, there's a whole theory about determinants in linear algebra, which I'm not going to discuss here. The short version of it is that you can calculate the determinant of a matrix as A times D minus B times C, where A, D, B, and C correspond to these elements in the matrix, okay? So it's this element times this element minus this element times this element. Now, in the Hessian matrix, we have this special type of symmetric matrix where these two are the same. So in fact, you could even simplify it to be this times this minus this squared. Anyway, you don't actually need to implement the determinant calculation yourself. There is a NumPy function that calculates the determinant of a matrix. Okay, and you can confirm that once you've found that linear algebra function for calculating the determinant in NumPy, then set it up with these numbers here, and basically you should get the answer that the determinant of this matrix is minus 11. So that is 1 times minus 1, which is minus 1, minus 2 times 5, which is 10. And so that gives us 11. So this is just a quick confirmation that you have implemented the code correctly, and you know how to use the NumPy function corresponding to a determinant. All right, so here we are back in Python. Here I'm creating sim.matrix. So this is a matrix object, and we have matrix elements in the first row of fxx, and then we have the cross terms xy, and here we have the other cross term yx, and this is the second partial derivative of y, and then again with y. Okay, and actually let me, I'm just going to show you what this looks like first. Okay, so here you see this matrix H is pretty complicated. It's a 2 by 2 matrix. There's a ton of things going on here. But this whole expression right here, this ridiculously long expression, this is the function for the second order derivative with respect to x twice. Okay, so this is fxx. This is fyy. And this term over here, including the denominator y, and this term over here, these are fxy and fyx. And you can visually easily confirm that these two are the same. Okay, so that is the symbolic representation of the Hessian matrix. And now what we do is show this particular matrix using substitution, substituting in for variable x, the value of x val, and variable y, the variable y val. And that's what I defined here. Okay, so this gives us the symbolic representation. And if you want, you can look at the actual numbers, eval f, or I guess those are the actual numbers, but these are the numerical approximations to those numbers. Okay, very good. So now to get the determinant, you can use the function in NumPy, numpy.linalg, this is for linear algebra, and det is for determinant. And here I'm implementing this little matrix that I showed in the book. And yeah, again, that's just to confirm that we get the right answer. Don't worry about this. I think this is just a bit of a rounding error. Now for the sixth and final part of this exercise. Here we want to create an image of the Hessian determinants. Now, the determinant, as we've calculated it here, gives us one number for each matrix, each numerical matrix. Okay, so this is not a matrix of functions. This is a matrix of 4 numbers. And those 4 numbers can be obtained for every value, every pair of x and y coordinates that we can substitute in for the Hessian matrix. Okay, so the idea is to create a new matrix of determinants that looks like this. Now here, x and y have the same coordinates as the original function and all of its derivatives, partial derivatives that we have calculated and also visualized. So what you want to do is loop through all of these values here of x and y. And for each pair of values, so for example, x equals 1 and y equals 2, that is this value over here. For that specific pair of xy values, you can implement the, or calculate the Hessian matrix. And this is a 2 by 2 numerical matrix from which you can extract the determinant. And whatever that determinant value happens to be, that is the number that corresponds to this element over here in this Hessian matrix. I hope that makes sense. If that's still a bit confusing, then I think it will be clear when I show you the code. Okay, so here what I do is lambdify the Hessian matrix. This is H, the symbolic Hessian matrix. And we're lambdifying with 2 variables, x and y. And now we loop over, we have a double for loop over all the values of x and all the values of y. And inside this double for loop, for each element in this matrix, we substitute in, so we evaluate this Hessian matrix for this particular value of x and this particular value of y. And then we calculate the determinant and store that in this matrix D, which you can see is initialized to zeros of the same size as the matrix that we have been working with. Okay, and here is, just in case you are curious, you can see how much faster it is to lambdify something than to use substitution. This is something I've discussed multiple times before in the book. Basically, the idea is if you only need to evaluate a symbolic expression once, maybe twice, then, this is fine. This method works great. But if possible, and if you are going to be doing a lot of calculations, this lambdification is way, way, way super a lot faster. Now, you don't really notice the change in computation time if you're only running, a very small number of calculations, which is why it otherwise doesn't matter. But here we're doing lots and lots of calculations, and so so the speed here really makes a difference. Okay, here we go. This is what the matrix looks like. Now, this is a like weird bogus two variable function, so this image on its own is not interpretable, but we can say that, these outlines here, especially where this is 0, these correspond roughly to inflection points for single variable functions. As I mentioned earlier and discussed in the book, if you are working on advanced computer vision and image processing or multivariable optimization, then you might encounter the Hessian matrix.